Imagine for a moment that you bought, I don't know, a vintage sports car, a classic.
Okay.
You drive it for 20, maybe 30 years. It's fast, it's sleek, it gets you where you need to go. But the manual, the one from the original engineers, it has this terrifying clause.
No.
It says that after mile marker 40,000, the engine block is sealed. You can't repair it, can't swap parts, you certainly can't upgrade it. From that point on, things just rattle loose until it stops running.
Wow.
For over a century, that is exactly how the scientific community viewed the human brain.
It really was the prevailing dogma, and honestly, it painted a pretty bleak picture of aging.
A very bleak picture.
The theory was called cerebral fixity, which is a mouthful, but you could just think of it as the one-way street model. You hit a peak in early adulthood, and then
It's all downhill from there.
a long, slow slide. The belief was absolute. Once a neuron was gone, it was gone for good.
Yeah.
The brain was just a static machine that could only degrade.
Which is such a heavy thought to carry around, especially if you're, approaching retirement. It basically says your best days are biologically behind you.
Right.
But the reason we're doing this deep dive, and the reason I'm actually so excited about this research, is that we are looking at a total paradigm shift. We're moving from that old fixity model to something they're calling lifelong malleability.
Exactly. The sources we have suggest the brain isn't a fixed machine at all. It's more like a riverbed that's constantly shifting its course. We're calling this the brain's second act.
Second act has a nice ring to it, but I want to be careful here. Is this just, toxic positivity? Are we just saying you can still do crossword puzzles, or is there legitimate biological change happening?
That's a fair question.
Our mission today is to figure out if neuroplasticity is actually strong enough to change the quality of life in retirement. Can we move from passive aging to what the literature calls intentional engagement?
And that distinction is the key.
Yeah.
Passive aging is letting biology happen to you. That's the old car manual. Intentional engagement is using these mechanisms of neuroplasticity to actually shape your biology. And to answer your skepticism, yes, the biology is real. This isn't just about feeling better. It's about physically rewiring the organ inside your skull.
Okay, so let's start with that buzzword, neuroplasticity. I feel like I see it on every app that promises to make me a genius in 5 minutes a day.
It is everywhere.
If we strip away the marketing, what is actually happening? Chemically, structurally?
Simply put, it's the brain's ability to reorganize itself. It modifies neural connections in response to, experience, learning, even injury. But here's where we need to get specific, because plasticity isn't just one thing. The research breaks it down into two types, structural and functional.
Okay, let's pause there. That's an important distinction. If I'm listening, I'm probably wondering, am I building a bigger brain or just a faster one?
It's actually both, but they happen on different timelines. Think of structure as the city map. Structural neuroplasticity is about changing the physical stuff.
Geography.
The geography, exactly. Growing new dendritic spines, those are the little receivers on your neurons. Or even increasing gray matter density. You are literally paving new roads.
So that's the hardware. You're physically renovating the house.
Exactly. And that takes time. Functional neuroplasticity, on the other hand, is more like traffic control.
Okay.
It's about how efficiently the roads you already have are working. You're not building a new lane yet. You're just synchronizing the stoplights so traffic flows better.
Which would explain why you might feel sharper at a new card game way before your brain would, physically change on a scan.
Precisely. And this leads us to one of the biggest mythbusters in our source material, the idea that adults cannot grow new brain cells. For the longest time, we thought
There's a birth of new neurons.
Right, we thought that stopped after childhood.
I remember my teacher saying, don't kill your brain cells, they don't grow back.
We all heard that. But the research is clear. Neurogenesis continues throughout life. But, and this is a big but, it doesn't happen everywhere. It happens in a very specific region called the dentate gyrus of the hippocampus.
Which is super convenient because the hippocampus is basically the headquarters for learning and memory.
It is the headquarters.
Right.
But, here's the catch. It operates on what's called the Hebbian rule.
I've had this one. Neurons that fire together, wire together.
That's the one. It's catchy, but in practice it means the brain is an efficiency expert. If you repeatedly stimulate a pathway, say, by practicing a new language, those connections physically strengthen.
But the reverse is also true.
The reverse is also true. If you stop using them, the brain prunes them away. It's literally use it or lose it. And this whole process is supported by a protein called BDNF.
Brain-derived neurotrophic factor. Our outline calls it fertilizer. Is that a good way to think about it?
It's a decent shorthand. Maybe think of it more like a signal flare that tells the brain, hey, this connection is important, keep it alive. It supports the survival of neurons and encourages new synapses. Without it, that structural road building,
Hmm.
it just doesn't happen.
So we have the mechanism. We know the brain can change. But why does this matter so much as we age? This brings us to a concept in the research called cognitive reserve.
And this is where it gets really fascinating.
Okay.
Have you ever wondered why two people can have the same amount of age-related brain changes? Maybe an autopsy shows they both had significant Alzheimer's plaques.
But in life, one person showed severe dementia symptoms and the other seemed perfectly sharp until the very end.
Exactly. That's the reserve at work. It's like a buffer.
Right.
And we need to differentiate between brain reserve, which is just the passive hardware, how big your brain is, how many neurons you have, and cognitive reserve, which is the active software.
The flexibility.
The flexibility and the efficiency of your networks. High cognitive reserve lets you cope with pathology. Your brain essentially says, okay, this main highway is blocked by damage. Fine, I know 6 different back roads to get to the same memory.
The sources mention a specific theory for this rerouting called the scaffolding theory of aging and cognition, or STAC.
Stack. It basically posits that as the brain ages, it builds, well, scaffolds. It recruits alternative neural circuits to maintain performance. A great example of this is something called PATAC.
The posterior to anterior shift in aging, so back to front.
Yes. Younger brains tend to use the back of the brain posterior regions for things like sensory processing. But as we age, those regions might degrade a little. So the aging brain compensates. It over-recruits the frontal regions.
The prefrontal cortex, the thinking and planning part.
Exactly. The executive center has to step in and help out the sensory center. It's the brain actively working harder, shifting the load to the front just to get the same result. It's a brilliant adaptation.
Okay, but this brings me to a contradiction I saw. Usually when we see an older brain lighting up like a Christmas tree on a scan, we think, wow, look at that. That's great.
Right. Look at all that activity.
But based on what you just said about scaffolding, that extra activity it's actually the brain struggling to compensate.
You've hit on a critical point.
Yeah.
Often, that upregulation, that increased activity, is a sign of inefficiency. It's the brain having to call in the reserves because the primary team can't handle the load. But
There's a but.
there's a massive but, and it comes from a really fascinating place: musical training.
This was my favorite part of the deep dive. We have a longitudinal study here tracking older adults over 4 years. Some played instruments, some didn't.
And this study is a goldmine. It's so rare to track people for that long. They compared a continue group, people who kept playing, versus those who stopped. And the continue group showed better preservation of verbal working memory.
Which is huge.
Huge.
Yeah.
And more gray matter volume in the right putamen.
But the real surprise was in the connectivity. Right, because based on that scaffolding theory, you'd expect the musicians' brains to be firing on all cylinders, recruiting every backup system they have.
That's what the compensation hypothesis would predict: more effort, more activation. But that is not what happened. The older musicians actually showed lower connectivity between certain parts of the brain compared to non-musicians.
Hold on, I want to push back on that for a second.
Yeah.
In almost every other area of fitness, more is better. More reps builds muscle, right? Why, on a brain scan, is less activity considered a win?
That is the intuitive trap. When you see a brain lighting up on an fMRI, it looks impressive, but biologically, it's expensive. It burns a ton of glucose. It's metabolically taxing.
So a loud brain is actually a struggling brain.
Often, yes. It's like a car engine redlining just to maintain 60 miles per hour. What the musicians showed is what they call the holdback upregulation hypothesis. Because of all that training, their primary neural networks were so robust, so efficient.
They could hold back that frantic compensatory
They
activity.
didn't need the scaffolding.
The wall was still solid.
Exactly. Their neural patterns looked much more like the brains of younger adults. They were solving the problem with a sniper rifle instead of a shotgun.
That's incredible. And the studies specifically noted this helped with speech and noise perception.
Which, as anyone over 50 knows, is one of the first things to slip. Trying to hear a conversation in a crowded restaurant, the musicians maintained that ability because their brains could filter the signal efficiently without overheating the whole system.
Okay, so learning an instrument is powerful, but not everyone is going to pick up the cello at 70.
That's fair.
What about something more accessible? The sources talk about a program called Stronger Memory, which involves reading aloud, writing, and simple math.
Right, and this study is crucial because it pivots us from just skill learning to the synergy of social learning. They had 2 groups. One did the exercises alone, the other did them, but also had a weekly social engagement component.
And the results, they weren't subtle.
Not at all.
Hmm.
Both groups improved, which is good news in itself. But the social engagement group saw significantly greater improvements in their cognitive scores. But even more importantly to me, they had a greater reduction in subjective cognitive decline.
They felt sharper.
They felt sharper and more capable, which is half the battle.
But why does the social part matter so much? Is it just that it's more fun, or is there something else going on?
It's deeper than just fun. It's about what's called the biopsychosocial model.
Yeah.
Cognitive health isn't just biology in a vacuum. Social interaction is incredibly complex for your brain.
How so?
Think about what we're doing right now. You're listening, you're watching my face for cues, you're anticipating when I'll stop, you're formulating a response. That is a massive real-time workout for your brain's processing centers.
So loneliness isn't just an emotional state, it's a lack of cognitive stimulus.
Exactly. And there's another layer, self-efficacy. The social group built confidence in their ability to succeed. If you believe you can learn, you're more likely to stick with it. That social support creates a powerful feedback loop.
So we have long-term music, we have social learning. But what if I want results, like now? The sources mention a study on language learning that was only 4 months long.
Yes, 16 weeks.
Can you really change your brain that fast?
Surprisingly, yes. This study looked at older adults, 59 to 79, learning a second language. After just 4 months, about 16 sessions, they showed improved global cognition.
And were there physical changes, or was this just that traffic control we talked about earlier?
It was primarily functional. They saw increased connectivity in key brain regions. Structural changes, like the actual volume of the hippocampus increasing, that takes longer. You're not going to build a new wing on the house in 4 months, but you can definitely rewire the electricity to make the lights brighter.
There was a detail in that study that felt a little unfair, though.
What was that?
Not everyone learned at the same pace. The participants who started with a larger hippocampal volume and better associative memory, they learned the vocabulary best.
Right. It does feel a bit like the rich getting richer. To get a better brain, it helps to already have a good brain.
Exactly.
And it does highlight the importance of starting with a healthy baseline. But I don't want the listener to be discouraged by that. It just emphasizes that we need to prepare the terrain. You can't plant a garden in concrete.
And preparing the terrain is a perfect segue to our final section, lifestyle modulators. We've talked about the work, the learning, but we need to talk about the environment of the brain. The sources hit 3 pillars: activity, diet, and sleep.
Right. We can't just demand our brains learn if we aren't fueling them properly.
Let's start with physical activity. We all know exercise is good for the heart, but you called it a primer for neuroplasticity. How does doing a squat help me learn French?
It comes back to that fertilizer, BDNF.
Yeah.
Physical activity, especially aerobic exercise, spikes your BDNF levels. It also increases blood flow directly to the hippocampus. So if you go for a brisk walk before you sit down to learn your Italian vocabulary, you are chemically priming your brain to be more receptive to that information.
That is very actionable advice. Walk, then learn. What about diet? The sources mention polyphenols.
Polyphenols, yeah. These are compounds in berries, dark chocolate, green tea. We usually hear about them as antioxidants, but they do more. They actually interact with signaling pathways that help neurons survive. They basically make your brain cells more resilient to stress.
So it's about creating a chemical environment where plasticity is even possible.
That's a great way to put it.
And finally, sleep. I feel like this is the one we all sacrifice. But the research here is very specific about why that's a terrible idea.
It is absolutely non-negotiable for the aging brain. We need to talk about the glymphatic system.
I've heard this described as the brain's cleaning function. What's actually happening?
Your brain is extremely active during sleep. When you enter deep, slow-wave sleep, the space between your brain cells actually expands. Some studies say by up to 60%.
Wait, the cells physically shrink to make room?
Essentially, yes.
Yeah.
This allows cerebrospinal fluid to wash through the brain tissue, and it flushes out metabolic waste. Things like beta amyloid, which is a protein we know is associated with Alzheimer's.
That totally changes the perspective on an all-nighter. You aren't just tired, you're leaving the trash to pile up in the kitchen.
That's a visceral but very accurate way to put it. And if that waste accumulates, it creates an inflammatory environment. You can't build new structural bridges if the construction site is filled with toxic waste.
Before we wrap up, there was a brief mention of technology. Things like TDCS, transcranial direct current stimulation. Is this sci-fi?
It's real, but it's still emerging. TDCS uses weak electrical currents to prime the brain. Imagine warming up a muscle before you lift. TDCS kind of warms up the neurons so they fire more easily.
Yeah.
It can make the brain more receptive to training.
But it's not a magic bullet.
No, the experts caution that this is a booster, not a replacement. You can't zap your brain into fitness if you aren't doing the work of learning and living healthily.
So let's bring this all together. We've gone from the really depressing idea of cerebral fixity, the car that can't be fixed, to the empowering reality of the second act.
It really is a complete reframe. We know now that the brain is capable of structural remodeling, growing new connections, and functional reorganization, becoming more efficient well into retirement.
And we have a recipe. It's not one thing. It's a multi-domain approach.
Exactly. You need novelty. That's the music, the language, the new skills that challenge the brain. You need social engagement. That's the multiplier effect that builds confidence. And you need physical health exercise, sleep, diet, to support the underlying biology so those changes can actually stick.
It's empowering because it puts the ball in our court. We aren't just passengers on this ride.
And that leads to a final thought I'd like to leave you with. We've talked a lot about cognitive reserve, which is often described as building a dam to hold back the flood of aging.
Right.
But I want to challenge that slightly with the concept of brain maintenance.
What's the difference?
Reserve is about coping with damage, using the side streets when the highway is broken. Maintenance is about preventing the damage in the first place. That holdback effect we saw in the musicians. It suggests we aren't just building a dam. We might be able to maintain the riverbed itself.
So we aren't just withstanding the storm, we're reinforcing the shelter.
Exactly. The science suggests that by actively engaging, by writing our own second act, we can do both. Aging isn't just a biological event we endure, it's a narrative we can still write.
That is a fantastic place to leave it. The second act is yours to write. Thanks for joining us on this deep dive.
It's been a pleasure. Keep learning.
We'll see you next time.